Hello, once again, thank you for joining us. This is the Space Nuts Podcast, episode 243. My name's Andrew Dunkley, your host, and with me is Professor Fred Watson, astronomer at large. Hello, Fred.
Hi, Andrew. How are you doing?
I'm very well, thank you, sir. Yeah, good. How are you?
Yeah, very well, thank you. I've been hearing that up in your area there's a mouse plague. Have you got mice at your place?
I've had one or two, but I've got little stoppers in the weep holes in the house that stop them from getting into the ceiling, which is where they tend to love to go and prattle around in the middle of the night, making little noises. But I haven't had that problem. But my son's place has had quite a few. Mm-hmm. One of my work colleagues has been catching them by the ton. Another of my colleagues, this will make you laugh, he's got a swimming pool and he's figured out the perfect mousetrap. Mice love to get into tight spaces because they feel safe. So he's got all the 1 metre tubing from his pool vacuum, and he's got them draped over the pool. So and he's got them surrounding the pool. So the mice crawl into the end of the tube and fall out the other side and drown. And then he just scoops them all up in the morning. But my wife's had some customers in her shop that have had, they've been catching 50 or 60 a day in the house, and 50 or 60 a day drowning in the pool that just fall in by themselves. So that's how bad it is. It is horrific further west, but there are lots in Dubbo at the moment. And the other thing that's happened, we now have locusts. So we've got locusts and we've got mice all at the same time.
Right, okay. Oh, that's what I didn't want to hear, because I'll be driving up there tomorrow.
I've been through a couple of locust plagues before, Fred, and I can tell you, if you exceed 50 kilometres an hour, they splatter on the windscreen. So if you drive all the way from Sydney to Coonabarabran at 50, you should stay clean. It'll take you 12 hours.
Well, I know, yeah. Oh, gosh, that's something to look forward to. I've experienced that before, and I do remember.
And they stink.
They stink, yeah. It's a really weird smell. It's kind of grass and dead animal. It's very odd.
Yeah, it's a musty, gnarly smell. And when they die in great numbers, they tend to all die in the same place, and the smell just gets worse.
Well,
hopefully we haven't got a big plague, but there are a lot of them flittering around the town at the moment, unfortunately, and a lot of green grasshoppers too. We noticed we've got a bit of a plague of those too. So the cats and the birds are going to be pretty fat by the end of the season, I think.
So you've got all these plagues, but we've probably lost all our listeners now. They're all
I guess so. Yes.
This is welcome to rural New South Wales, everybody. That's what it's like.
That's it. Now, coming up on today's episode, we'll get there eventually. We're going to talk about, strangely enough, the Perseverance Rover. Only because something's happened, and it's a good thing. We're also going to look at organic chemicals that are essential for life, having been found on an asteroid. And yes, it is that Japanese mission. They're starting to get some data from that. I love the next story, Fred, and you knew I would. Yeah. Somebody's come up with a model for a real warp drive. I am so thrilled. I am so thrilled about that. And we've got some audience questions from Hugh in Texas and Luke in the Netherlands, which we'll get to a little bit later. And they're good questions too, but they generally always are. We don't often get a dud, but if we do, we probably wouldn't use it. So if we haven't used your question, it was a dud. No, that's not true. That's not true. But let's talk about Perseverance, Fred. Where's it up to? I actually saw the other day they were trying to map out a journey for it, and they'd come up with two paths. One was safe, but the other one was more likely to give the results they were looking for, and they were trying to choose which way to go. Option 2, better data probably, but much more dangerous. So I don't know which way they went, but have they started moving?
I don't know the answer to that either, but I do know, yes, they have started moving. They've put 6.5 metres on its odometer.
Woohoo! Yeah. Well, see, now it's only worth half the price at the trading.
Yeah, that's right. So what they did was they rolled forwards 4 metres. Then they did a 150-degree turn, and there's pictures that show you, the effect of that with the wheels doing the turn. Because with a 6-wheel rover, each independently controlled. You can just turn on the spot. So they turned 150 degrees and then drove backwards 2.5 meters. So it's now got 6.5 meters on the clock. Exactly as you said, it will be worth half the price.
If they drove backwards, that would rewind the odometer. So the price just went up.
I suspect that doesn't work in Perseverance's case, because probably a lot of its trip travel will be backwards. In fact, I remember, I think it was Opportunity had a damaged wheel, and for a long, long time, many years, it could only go backwards.
Wow.
To drag the wheel that was stuck. One other bit of news is, and that might interest you, it's not a name I know, but NASA has announced the name of the landing site, because these, when you land a rover, you name the site, and it is called the Octavia E Butler landing. And Octavia E Butler apparently was an award-winning American science fiction writer who died in 2006, very young. He was only 58. Right. So, I beg your pardon, she was only 58. I do beg your pardon. I'm sorry, Octavia. I should have recognised that with an A on the end. Yes, she was an award-winning American science fiction writer, and as I just said, she died in 2006. And I'd never read any of her stuff. I don't know whether you have.
No, I can't say I have. The name is familiar, but I don't think I've read any of her work. There aren't that many female sci-fi writers around. There have been a few, but
that's right, and that's why
it seems to be a genre favoured by men and small children. But I'll look up some of her work. I'll be interested to see it.
Check it out.
Speaking of which, my latest is half proofread, if that makes any sense.
Good. That's all right. No, I do get that. I understand.
Yeah. All right. So Perseverance is on the move. I suppose there's still a lot of systems checking to do and bits and bobs to deal with before it really gets underway and starts its epic journey around the river delta.
Exactly. No, we're going to get daily reports from now on, and indeed we already have. So, sounds good. We'll keep our listeners, both of them, up to date with what's happening with Perseverance.
And that's you and me. We're both the listeners. Yes. We haven't used that joke for a while, so it's probably good to dust that one off, get the Martian dust off it. Yes, exactly. All right, moving on. Organic chemicals that are essential to life on Earth found on the surface of an asteroid. This has come out of that fabulous JAXA mission, which we talked about not so long ago when it came back down to Earth. This is pretty exciting. It
is, but it's actually the previous JAXA mission, the one that...
previous JAXA mission, right, yeah. That's right. They've got more than one. I keep getting...
Yeah.
I just keep putting them all together.
So it's Hayabusa, the name of the mission.
Yep.
We talked about Hayabusa 2, which visited the asteroid Ryugu, and yes, they've brought samples back, and remember they landed in Australia. But the first mission came back in 2010, and you might remember it was an epic journey because they either lost contact with or lost control of the spacecraft, and thought that the mission was lost, but some clever person thought of a way of taking the spacecraft on a long journey through the inner solar system. I think it had a flyby of Venus, and took it 2 or 3 years longer than they expected originally, but it did come back, and it had soil samples from the asteroid on it. An astonishing story.
Amazing story.
It is. So what's happened is scientists at Royal Holloway, which is a London university, have basically found, for the first time on an asteroid of this type, they found water and organic material. Now the water's locked up as a hydrated mineral in the soil sample, but the organic matter is stuff that contains carbon, and I'm not sure exactly which organics are there actually in the report I've read, but they would likely, there'd be all the usual suspects, the ones that have strong hydrogen carbon bonds, all the things that we're made of here on planet Earth. So, but what is interesting them, this work as well comes from a single grain of dust, Andrew. It's just amazing what these scientists can do. There's some really interesting aspects to it. First of all, it's not, the C-type asteroids, as they're called, are the ones that are carbon rich, and that's where you would expect to find carbon-containing chemicals, the kind of stuff that life is built from. But this is an S-type asteroid. Now, if I remember rightly, and I should know this because I wrote about it not long ago, I think that's stony. I might check that just to make sure. But it's not the kind of asteroid that you would naturally expect will be rich in carbon. But sure enough, it's there. And the really interesting thing is that when you do the analysis, the kind of analysis that they've been doing at Royal Holloway, and this is in the Department of Earth Sciences, they can tell what the grain has been subjected to, what the organic matter has been subjected to, and what they're saying. And this is actually Dr. Queenie Chan, who's at that Department of Earth Sciences. I'll just read what she said because it's very interesting. After being studied in great detail by an international team of researchers, our analysis of a single grain, nicknamed Amazon, has preserved both primitive or unheated and processed or heated organic matter within 1,000th of a centimetre of distance, 10 microns. Wow. That's about this, it's a fifth the diameter of a human hair. Yeah. So you've got unheated and heated matter directly, essentially in contact. So she goes on to say the organic matter that has been heated indicates that the asteroid had been heated to over 600 degrees Celsius in the past. The presence of unheated organic matter very close to it means that the infall of primitive organics arrived on the surface of Itokawa after the asteroid had cooled down. And so what she's saying is studying Amazon has allowed us to better understand how the asteroid constantly evolved by incorporating newly arrived exogenous water and organic compounds. I think that might mean comes from outside. These findings are really exciting as they reveal complex details of an asteroid's history and how its evolution pathway is so similar to that of the prebiotic Earth. So it's fantastic stuff, and she goes on to talk about what we've just been saying. The success of this mission and the analysis of the sample that returned to Earth has since paved the way for a more detailed analysis of carbonaceous material returned by missions such as JAXA's Hayabusa 2 and NASA's OSIRIS-REx mission. That's not yet back. Both of these missions have identified exogenous material on the target asteroids Ryugu and Bennu, respectively. Our findings suggest that mixing of materials is a common process in our solar system. So what it's saying is that organic matter is everywhere, and that I think is really a remarkable finding.
Didn't I say that though? Didn't I? Like I was comparing that probability in space to the way life gets a foothold on Earth, where you find weeds growing in cracks in cement in weird places, or the life just seems when it gets a foothold, it goes berserk, and that's certainly evident on Earth. Why shouldn't it be evident beyond Earth? And this sounds like it is telling us just that. By the way, you were right. S-type asteroids are considered indicative of stony. Stony is the word that they use in the description in the Wikipedia article I just found. But the other question that pops into mind is, if this sounds like it's a fairly common thing, that this organic matter exists, and the seeds of life seem to exist on asteroids, does that mean that it's very likely that Earth was seeded by asteroids and thus life grew here as a consequence of an impact?
Maybe, that's right. I mean, the thing is that I've got to be quite clear, we're talking about prebiotic life. In other words, prebiotic chemicals. It's not life. It's the things that make up the amino acids, which are an essential part of life, and they go on to be part of proteins. Excuse me. So what it's saying is that the raw materials are widely spread. But the big step, of course, is the one that we don't understand. How does a bunch of chemicals become a living organism? And you've got, you know, I mean, in our case, we've got the DNA, which is the hallmark of life in a way. It's in all living organisms. How do you get from these fairly complex carbon-containing molecules to these long string molecules that's got a genetic code in them? That's a process that really I mean, the evolutionary biologists probably have got some handles on it, but for random scientists like me, I think it's still largely an unknown process.
Yeah, it's one of the great mysteries, isn't it? But this could be a clue, building block to finding the
that's exactly right.
answer. Yeah. Well, that's very good news. And, of course, analysis of those other two missions ultimately will perhaps add to the knowledge and give us a few more clues to work with. And if we go out there and find evidence on the next 100,000 or 1 million asteroids, we might get 10% of the answer. Who knows? It's one of those things.
Could be.
All right. There certainly will be more to come on that with Hayabusa 2 and the Osiris-Rex missions yet to be fully analysed. In fact, the Osiris-Rex isn't back yet, you said, I think, Fred.
Yeah,
it's yet to return. You're listening to the Space Nuts podcast, episode 243, with Andrew Dunkley and Fred Watson. Thanks for joining us on the Space Nuts podcast, and thanks to our patrons. Growing in number, I think we're getting half a new patron per week on average. Probably a bit more. But no, we appreciate your support. You can certainly show your support of the Space Nuts podcast voluntarily by going to our website, spacenutspodcast.com. Click on the Support Space Nuts button at the top right-hand corner, and it will give you all the options. So just choose one, like you go to our Patreon. I'll click on that, and it'll open up the Patreon page and tell you what the subscriber options are, or you can do it through Supercast or Acast. It's as simple as that. But the ultimate goal is to make the podcast 100% listener focused through patrons rather than the commercialised approach. And you know, if we can achieve that, fantastic. It won't be a fast process. But if you would like to sign up and put a few dollars a month into the podcast, that would be wonderful. But as I've always said, it's totally voluntary. You do not have to do it, and we will never make you do it. But you know, the option is there if you feel strongly enough about the podcast, and we value your support. So thank you. Okay, moving on, Fred, to our next story, and this one I love. Some researchers have come up with a model for a warp drive. Star Trek, eat your heart out.
Well, that's right, yeah. So these are researchers. I'm not sure where they are, actually. What it's appliedphysics.org. Now, I'm not sure what appliedphysics.org is, but two physicists there have essentially produced a mathematical model for how a warp drive might work, and one that would not contravene the laws of physics. And they published it in a reputable journal, Classical and Quantum Gravity, which is something I haven't looked up. But the bottom line is that the idea of a warp drive, of course, comes from Star Trek and science fiction. Yeah. The idea is you're warping space and time in order to effectively exceed the speed of light. Even though you're not travelling faster than the speed of light, you're basically warping space so that you seem to get there faster than the speed of light, if I can put it that way. I know that sounds like gobbledygook, but that's the point. Now, it's back in the 1990s. I'm amazed that I'd forgotten it was so long ago. Something called the Alcubierre. I'm not sure whether I'm pronouncing that right, but Miguel Alcubierre basically proposed the idea of a warp drive back in 1994. I always think it's only a decade or so ago, but it's like a quarter of a century ago. And what the suggestion, this was some work that was done, I've got a feeling that was in the UK, although it's not a terribly British name, but of course it's researchers get everywhere. The idea was that you build a spacecraft that somehow can warp space, and it contracts the space in front and expands it behind of the spacecraft, and that lets you get around much more quickly. And I do remember the flaw with this, because I looked at it in some detail back at the time. It turns out that you need more than the entire energy budget of the universe to do this. That was the problem. So it doesn't work. It's not something that's ever going to happen. And so these two authors, whose names are Alexei Bobrik and Gianni Martir. Once again, I hope I'm pronouncing those names correctly. What they've done is they've said, let's just use bog standard gravity, a normal gravitational force. And if you've got something the mass of a planet, but the problem is it's got to fit into a spacecraft, then you can tinker around because of the curvature of space that you get by this huge gravitating mass next to you. I'm not clear from what I've read how they actually do that. So the deal is that you've got to find a way to compress the mass of a planet into a box, put it in your spacecraft, and then you can sort of work out where things go from there. And I don't know the details of that, but of course, compressing the mass of a planet into something that small, the only way you can do it is to turn it into a black hole. And well, a black hole the size of the Earth, I think we might have talked about this before. If you've got an Earth mass black hole, it has an event horizon, as all black holes have, and if I'm remembering correctly, and I think I am, the event horizon is 18 millimeters in diameter for a black hole the size of Earth. For a supermassive black hole, it's bigger than the solar system, the event horizon diameter. But for an Earth-sized black hole, it's small. Now, I guess your first problem is going to be, I'm just following on from the idea of having something like that lurking in a spacecraft. Your first problem is to stop it spaghettifying everything, because
that could be an issue.
Black holes do, and so that might be the penalty you pay for effectively faster than light travel. That you're spaghettifying not only yourself but the entire spacecraft. This report I might mention is on the physics.org page, which is a reputable physics source, but there's a lot of commentary underneath it. The user comments are fairly scathing of this article. The first one is, this makes physics people look like they believe in fairy tales. So it's really worthwhile reading those things. There's some interesting comments. No evidence has been found that time has an actual real existence. Time is nothing but mathematics, and that's a well-known principle within relativity. It's very, very interesting. Not only the article itself, but the comments that it has generated.
I seem to recall in the science fiction novel Dune that they used the same kind of approach to travel. They described it as travelling without moving, because what they did was they folded space. So you'd get into the spaceship, and then these weird wormy-like creatures would use some kind of spice to create an effect that folded space, and you ceased to be where you were, and you were suddenly
somewhere else, light
years away in another part of the galaxy. So the folding of space, or the warping of space, is not a new theoretical concept. It's been around in science fiction and in situations like this for years. But I suppose that the question is, are we ever realistically going to be able to do what needs to be done to achieve it? And it sounds like it's a real long shot at the moment. I mean, in theory, it's doable. In theory, it's It's possible, but practicality is something that suffers, I think, when you're trying to compress the mass of a planet into a box.
Exactly, without any kind of unintended consequences.
Indeed. And I imagine there would be many unintended consequences when you're playing with that kind of energy. But look, at least they've put some thought into it. And who knows? One day we may well crack it, especially if we can answer some of the questions of particle physics, and that opens doors. And you just never know, Fred. If you go back 200 years in a time machine, which is another thing they haven't invented yet, and tell people, oh, we went to the moon in 1969, they would go, yeah, right. What did you build a big ladder? Never say never about anything. There's so many mysteries in the universe that are unanswered because we haven't developed the knowledge or understanding yet, but the time may come. We beat flight. In fact, I think flight as a human achievement is probably the greatest thing we've ever done, because we went from the first flight to standing on the moon in a massively short period of time. It was just incredible that humanity could have gone from there to there in
half a century.
Yeah, exactly right. Basically half a century. Yeah, it's unthinkable. I mean, that kind of advance in technology is phenomenal. I think it's amazing. So never write off warp drive. I think there's hope. I do think there's hope.
I agree with you, actually, Andrew. Especially when we're looking at what the particle physicists are talking about. Quantum gravity is something that we'll understand at some stage. We don't at the moment, but that could open up all kinds of doors that.
Who knows? And it reminds me, I caught an article recently about another study that suggested there are natural wormholes in the universe that could well enable us to move around much faster. Not, warp speed, but definitely getting into other places more quickly. And I think you and I talked about that at one stage recently, about these sort of superhighways, I think they referred to them as, in space. So, there are many possibilities that exist for long-haul space travel. We'll probably never get to do it, Fred, but one day someone will, I'm sure.
Maybe
all right.
So. Maybe so.
This is the Space Nuts podcast. You're with Andrew Dunkley and Fred Watson. This is Space Nuts, the podcast, episode 243. Andrew Dunkley here with Professor Fred Watson. Fred, we've got some questions, and this one comes from Hugh in Austin, Texas, where he said the polar vortex has finally let us go. I can sympathise with what you've been through this last winter. Saw a lot of the footage of the big freeze, and no thanks. No, I'm very happy where I am, where I never see snow or ice, or maybe a bit of frost from time to time, but that's about as bad as it gets here. Anyway, Hugh says, I've been a listener for some time now and continue to love your podcast. Well, somebody does at last. Question, can you explain how it is possible to know the age of the universe since, as I understand it, the universe may extend far beyond our ability to observe it? How can we run back the clock on the universe's expansion if we don't know for certain how big it is? I know scientists have thought about this, of course. I just don't know how they've taken this into account. Thank you. Thank you, Hugh, for the question. It is a great question. I don't think we've tackled the age of the universe from this angle before. And as you and I probably talked about a week or two ago, there's a limit to how much of the universe we can see. We don't know how much of it exists beyond that. So, as Hugh suggests, how do we know how old it is if we don't know how big it is?
It's a great question, and I think you're right, Andrew. I don't think we've ever been asked this one before. We've been asked how you determine the age of the universe, but not how do you do it without knowing the size. And in fact, you don't need to know the size. What we can measure is the rate of expansion. And the rate of expansion is just, it's basically, a difference in size over a different distance a difference in time. In calculus, it's ds by dt. So it involves time in when you look at the rate of expansion. That's telling you something about time. And in fact, the easiest thing to do, and this is what physicists did before they really even thought much about the Big Bang. Georges Lemaitre, who was the guy who suggested that sometime in the distant past, because we observe the universe to be expanding, at some time in the distant past it must have all been in one place. And you can deduce what that time is from the expansion rate. In fact, you basically just turn it upside down. You put, you solve the equation. And you get, I think for, really early on, they got an answer that's not that far different from what we know now, about 15 billion years. But then in the 70s, people thought, well, we know the rate of expansion, but what we don't know is whether that rate of expansion has changed, and everybody assumed that the rate of expansion had got less as time went on because the gravitational pull of everything in the universe would slow the expansion down. And that created a problem, because then when you solved for the age of the universe, you got something that was less than the age of atoms and less than the age of planets, and that doesn't work. But of course now we know it's the other way around. In fact, the rate of expansion is increasing, so it's getting faster. But yeah, it's just about the rate. You don't need to know the size. All you need to know is how fast it's expanding, and you can get the age.
Yes, but in saying that the speed is accelerating, does that not create another question mark on the age of the universe? Do we know how much it's accelerating?
Yes, we do. That's measured. The trick is to measure it back in time as well. So it's fine knowing what the accelerated expansion is now, but you want to know what it was when the universe was half its present age, for example. And it turns out all those investigations show that after the Big Bang, and that period we call inflation, when the universe expanded by an enormous quantity, it settled down into an expansion that did initially slow down, Andrew, because the universe was compact and the matter in it was close enough that its gravity was able to overcome what we call dark energy, which is what's trying to make the universe expand more rapidly. And it was only when you get to about half the age of the universe, maybe 5 or 6 billion years ago, that you start to see the accelerated expansion. It's still a hot topic in cosmology. People are trying to solve exactly the way this has changed, but that's our best estimate at the moment, that for a while the universe did slow down in its expansion, but then it took off in a big way, and that's what it's doing now.
Yeah. So with the data we have and the knowledge we have, and all the mathematical equations that go into it, times 2 to the power of 10, we know, within reasonable limits, the age of the universe with confidence.
Yeah, you can put limits on it. The best estimates come from combining what we see in today's universe with the distribution of of galaxies, and combine that with what we read from the cosmic microwave background radiation, which is what the universe was doing at the age of 380,000 years. And when you put all that together, the answer is about 13.8 billion years, and I think it's plus or minus about 200 million years. Of course, there could be, huge uncertainties because of things that we don't know about. We don't really know that much about dark energy. We believe it's there, and we think we know how it works, but we don't know what it is still. That could put a spanner in the works in terms of the age. But with the best physical measurements we have so far, it's 13.8 billion years.
So why then I've read some articles in recent years that have put the number at 13.2 or 13.5 billion years. Why are they wavering on the number if we know, with certainty or some certainty that it's 13.8?
There is, so that 13.8 is the consensus, I guess you'd say. There is still, some people talk about a crisis in cosmology. because so the rate of expansion is something we call the Hubble Constant. That's the rate of expansion now. And when I was a young astronomer, Andrew, that the estimates for that varied by a factor of 2. In fact, there was one body of people that said it was 50 and one group of people that said it was 100. Doesn't matter what the units are. But once the Hubble telescope was launched to solve that problem, which it did, and the answer was approximately 75. So it was exactly halfway between the 50 and the 100. And that's still what it is, but there is still a little bit of uncertainty. You get some disagreement between today's galaxies and the cosmic microwave background radiation. And so some people might put a different number on it. But I think it's fair to say that the bulk of cosmologists, what you might call mainstream cosmologists, put it at about 13.8.
Okay. And that, I think I've found the gap, because you were a young astronomer about 13.5 billion years ago, and then the age of the universe is...
Yeah, something like that, that's right, exactly.
Sorry, Fred, couldn't help it. Could not help it.
Look, talk to me about time warp, I know all about that.
Oh dear. Okay, Hugh, thanks for the question. Hope we managed to help you out there. The next question's an audio question, and this one comes from the Netherlands. This is from Luke.
Hello guys, this is Luke from the Netherlands. I live near Leiden, near the observatory. And I live there together with an alien. But it could also be a dog, I'm not sure about that. Well, I have a question for you guys. I noticed that in space we find the same material and elements we also find here on Earth. For example, iron, water, carbon, and so on. My question is, are these materials completely the same in composition than, for example, the iron and the water here on Earth? Or are there differences? And are there elements found in space that we do not find here on Earth? Seems to me the universe is such a big space. Seems a bit unnatural that everything's the same. So, summarized, is everything the same in space regarding material? And have we ever find something due to material or elements that we do not find here on Earth? Well, thank you guys. Hope to hear from you. Bye.
Thank you very much, Luke. Appreciate the question. Now, before we get into the answer, that question is incredibly familiar to us, because we feel deep down we might have played it before, but we are so old we can't remember. And we like the question, so thought we'd run it anyway on the presumption we haven't played it before. But if we have, apologies, but I don't think we need to apologise, because it's a great question. It's a really good question about whether or not the stuff in space that's on Earth is the same as what we've got, and is there stuff in space that is not found on Earth? What are the differences, if any, of the shared materials? I like the question.
I do. I like a lot about this question. I like the fact that Luke lives near Leiden, which is very significant place in the history of the telescope. It was where Prince Moritz, in September 1608, trained the very first telescope that was in recorded history onto the, I think it was the windows of the church at Leiden. So it was really, it's a very important place, and of course there's an observatory there, as he says. Anyway, enough of that. That's all historical stuff. There is I guess one comment that Luke made there that I think almost solves the problem immediately. And he says, it seems to me that the universe is such a big space or a big place, seems a bit unnatural that everything is the same in terms of the chemical elements. But when you think about it, it's not, because the universe, and we've just been talking about this, was once a single point. Everything was effectively in the same place. So you've got this tiny, tiny thing that expands. It's a ball of energy, but it expands incredibly rapidly. And so we've 13.8 billion years later, you've got stuff spread everywhere. But it might not be seems quite so unnatural that all the chemical elements are the same, because they all started off at the same time and in the same place. And they started off with the raw material of, protons and neutrons and all that stuff. That was the first set of matter that was formed within the first 3 minutes, in fact. But there's some interesting questions in there that Luke has asked. One is, are there elements found in space that we don't find here on Earth? And it's that, as far as we know, the answer to that is no. But things have been discovered in space before they were discovered on Earth, and the classic example of that is helium, which was identified in the Sun in the 1880s, I think. It was round about the back end of the 19th century, by spectrum, by the fact that there was what we call an emission line at a wavelength that didn't correspond with anything, or a colour that didn't correspond with anything that we knew on Earth. And so that was identified. I think it was Lockyer was the astronomer in question. He was a very well-known British astronomer. It was identified as a new element and given the name helium, Helios, the Greek name for the sun, or the god of the sun. It was, I think it was William Ramsay was his name, a Scottish chemist who finally isolated helium on Earth towards the end of the 19th century or the beginning of the 20th century. So that's a situation where there's something that's completely unknown on Earth, identified in space, but then found on Earth. And there's actually a parallel story which had a less happy ending, and that's the story of nebulium. When people looked at the spectra of nebulae, which are gas clouds in space, this is going back to the 1860s, in fact, when William Huggins was the first person to do that. There's a whole lot of Williams in this story. He did the analysis, and he discovered that there are gas clouds in space because he could see that they had the signal of an excited gas rather than a star. They're completely different spectra. But he couldn't identify what the element was that was causing this, and so he got the name nebulium. They decided that because helium had been discovered in the Sun but was a real element, there must be something there in nebulae, which they called nebulium, which was not found on Earth. But it was unlike helium, which was discovered on Earth by chemical reactions. Nebulium never turned up. And it was a puzzle for the first quarter of the 20th century. It was something that people really sweated over, especially, and this is another key point in the answer to Luke's question, especially when the periodic table came along. So we could see where all the elements fitted in their atomic numbers and their atomic weights and things. You've suddenly got this complete atlas of the elements, and there was no space for nebulium. It couldn't be slotted in anywhere. And eventually, it was 1928, it was an American astronomer called Ira Bowen who figured out that what you were seeing were something called forbidden emission. And it's forbidden on Earth because we can't put a gas into the very rarefied form that you find it in space. In space, the gas behaves differently because it's almost a vacuum. And you can't replicate that vacuum on Earth. So the signature that you were getting from this gas, it actually was just oxygen. But with an unusual signature because it was so rarefied. Really great story. It's one of the great detective stories. So you can bark up the wrong tree. So nebulium doesn't exist. In 1928, it was demolished by Ira Bowen. It does. There is just one postscript to this, though, is that there is an important aspect where things do differ, and you and I have talked about this at length with the idea of isotopes, because isotopes are, they're different forms of chemical elements. So an isotope is a variant in a chemical element that's different from another one even though it's the same element, because it's got a different number of neutrons. Remember, neutrons and protons are in the centres of atoms. The proton is what gives you it's something called the atomic number. The number of protons is the atomic number, and that is the same for every element. So an atomic number defines the element. But if you've got a neutron number as well, that, in fact, I think it's called the mass number, if I remember rightly, and that actually can vary. You can get different isotopes. And so we've talked about the isotopes of hydrogen that you get, heavy hydrogen and normal hydrogen, and whether that can reveal where the water in the Earth's oceans came from. So some of the isotopes are found elsewhere, and I'm not sure that there are any in space that aren't found on Earth, but it just gives you a bigger variation in the periodic table.
And of course, when they created the periodic table, they left space in it for future discoveries. They had enough foresight to realise that they hadn't found everything. Someone way beyond them would. And
yes, that was at the end, though. That's kind of at the end of the periodic table. Yeah. But there's room there for adjustment. They've added to it many times in recent years. So very, very heavy nuclei, some of which don't last for more than a millisecond or something. They're not particularly interesting as building blocks of matter, but they are important.
So there you go, Luke. Everything's the same. It's all the same. It's like putting a corn kernel into a microwave and hitting start, and it turns into popcorn, but it's still got the same stuff. So that's my rudimentary example.
I think that's a very good one, Andrew.
Yeah. But appreciate the question, Luke. And don't forget, if you've got questions for us that you would like to ask using your voice or just using that, age-old text system called email, you can do so via our website, spacenutspodcast.com. Click on the AMA tab, and there are options there to record. If you've got a microphone on your device, you can record. Don't forget to tell us who you are, where you're from, or you can use the email interface to send your question through, which we had one of each today, which is good. So thank you again for those who've sent in questions, and we'd certainly appreciate a few more if you've got a question in mind. One more thing before we finish off, Fred, and I don't know if I triggered this by saying something in a previous episode, but I've been receiving dad jokes from Space Nuts listeners. This is very disturbing, very, very disturbing. One of them is a play on words that I love. This comes from Judd, who sent us a question recently. Two people in spacesuits talking to each other. I can't find any milk for my coffee. And the reply is, in space, no one can here use cream. And another one, I'll have to bump them both off because I really don't want to do another one ever again. This one came on Facebook, and forgive me, I've forgotten who sent it, but I love this one. If I had to rate the solar system, I'd give it 1 star. I do like that one. Yeah, that's I do like that one. But yes, don't make a habit of it, please. No, I don't mind. If you've got one, I'd dearly love to hear it, and we can share it on the Space Nuts podcast. People often say, how low can you go? Well, we can go pretty low on this program, as it turns out.
Yeah, we can.
All right. Fred, we'll wrap it up there. Thank you so much. It's been a lot of fun. Good to talk to you.
You too, Andrew. Always good.
And we'll catch you again next week.
Likely.
Fred Watson, astronomer at large, part of the team here on the Space Nuts podcast. Thank you for listening. Don't forget to tell your friends, say hi to your mum for me, and I'll see you again next week on another edition. Bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Subscribe to the full podcast on iTunes, Audio Boom, and Stitcher, or your favourite podcast distributor.
This has been another quality podcast production from Bytes.com.